What would happen to you if a black hole devoured you? Quiet and cool, reassuring and terrifying at the same time. And suddenly, you feel something tugging at you, heavy at first, but it becomes stronger as it pulls you into a far corner devoid of heaven. In the blink of an eye, you will have entered a black hole. Here, the universe becomes something else for you, says astronomer Priyamvada Natarajan of Yale University. With the publication of the first image of a black hole, there is no longer any doubt that these space-time monsters really do exist. But the division among physicists concerns what happens to a person's body if it falls into the mouth of a wormhole. So what fates await you if you're unlucky enough to come face to face with a black hole live? All things exert a gravitational pull on each other, and this force is weak in most cases. But in the case of a black hole, the pull is so strong that nothing, not even light, can escape by itself. The black hole is so powerful that time itself would fold inside it. You won't feel any different as you fall, but to the outsider, it will look like you're slowing down. As you scatter inside this space hole, all the photons that are pulled in turn with you will create an eye-blinding band of light that revolves around a hole of pitch black, as seen in the image of the Event Horizon telescope team. Two color effects will escort you to your final destination. Darkness clouds your eyes as you see the black hole expanding, and the surrounding stars blinking and collapsing. It's your last chance to escape. Soon, you will be facing the event horizon, the point at which it becomes difficult to resist the gravitational pull of a black hole. By the time you are able to see the event horizon, you will be able to see the curvature of the star bar around it, adds Natarajan. Convex streaks of light would wrap around the black hole, but as you accelerate toward no return, the momentum of the gravitational field will change the nature of the light you see. If your neck muscles have enough strength to enable you to take at least one look back, all the starlight behind you will seem to blend into a single reddish blob. In the meantime, the tranquility of outer space will turn into complete darkness, and you will feel that you are descending into a deep valley, but as Natarajan says, it is a valley without a bottom. And here your body begins its unique journey of torments. Gravity inside the black hole is so steadily building that it will not only crush you, but will pull every part of your body at varying speeds, resulting in spaghetti effects. If you fall to your feet first, your ankles will snap away from your knees before your neck will stretch into a linguine like spaghetti, but the difference in time will be small enough that you probably won't notice it, says Natarajan. The perfect expression since your eyes will pop up, then what happens to you? To choose, stay where you are. Go to 1 to choose. Wait for the black hole to burp. Go to 2. To choose, escape through a white hole. Go to 3. To select, I will try to radiate out of the hole. Go to 4-1. Hold your position. The laws of thermodynamics are ruthless, and even a black hole isn't immune to what you're doing. According to the second law, the amount of entropy or disorder in the universe cannot be diminished. So when your mutilated body falls into the hole, the entropy it contains cannot simply disappear, as it would increase the entropy of the black hole itself. But if a black hole has entropy, it must also contain heat, so, like any object that carries heat, it must radiate heat. How can radiation escape from an inescapable object? In 1974, Stephen Hawking came up with an explanation, by inventing radiation that bears his name instead of being emitted by the heat of a black hole, that Hawking radiation is made of particles and antiparticles that come into existence near the event horizon. And these pairs of particles and antiparticles always come into being scattered. These subatomic twins are intrinsically related, and any change leads directly to another. In the language of quantum mechanics, they are said to be entangled. Under this subatomic conspiracy, any antiparticle that slams into the black hole would have a partner particle that could escape, radiating away, reducing the black hole's energy. But this leaves us with a troubling conclusion. At some point, the black hole itself will radiate away, taking you with it. This vanishing behavior violates another fundamental principle of theoretical physics. Information cannot simply disappear. Even if we destroy information in one way or another, if we burn a book by throwing it into the fire, that information will still be available to be obtained from the smoke and ashes that remain, even if this form of the book is difficult to read. Physicists rely on this continuity to gain information about the past and make predictions about the future. If a black hole can destroy information, it can destroy any trace of you too. We wait for the black hole to burp. Some physicists have suggested that you could hold on to a black hole while it is being vaporized by Hawking radiation, see number 1, before it belches you as it takes its last breath. That way, At least some of your information won't be lost forever, but you'll still be keeping ions while the black hole slowly breathes. At some point in the distant future, depending on the size of the first black hole, the event horizon will be so small that no wave of light can cross it. At this point, the radiation carrying your remnants will no longer be belched out, leaving behind the empty space that was once occupied by a black hole. Just as black holes don't allow any object to escape their pull, and hypothetical objects known as white holes can't hold onto anything other than being emitted by the black hole's heat, this Hawking. Radiation is made of particles and antiparticles that come into existence near the event horizon. And these pairs of particles and antiparticles always come into being scattered. These subatomic twins are intrinsically related, and any change leads directly to another. In the language of quantum mechanics, they are said to be entangled. Under this subatomic conspiracy, any antiparticle that slams into the black hole would have a partner particle that could escape, radiating away, reducing the black hole's energy. But this leaves us with a troubling conclusion. At some point, the black hole itself will radiate away, taking you with it. This vanishing behavior violates another fundamental principle of theoretical physics: information cannot simply disappear. Even if we destroy information in one way or another, if we burn a book by throwing it into the fire, that information will still be available to be obtained from the smoke and ashes that remain, even if this form of the book is difficult to read. Physicists rely on this continuity to gain information about the past and make predictions about the future. If a black hole can destroy information, it can destroy any trace of you. The problem is that this flammable barrier completely contradicts Einstein's theory of relativity, which predicts that the event horizon of a black hole should not be different from the space around it. According to Einstein, gravitational pull should always be indistinguishable from the results of acceleration. If you were sitting in a rocket accelerating steadily through space, you would feel gravity pulling you firmly back into your seat. This principle of equivalence is supposed to occur at both ends of the event horizon, which means that you should not notice anything unusual while crossing it. But, even if we allow a wall of this kind to exist, it is not the best way out. If you were to get through it,